So, good evening everybody. The beginning of everything, as you can see from the subtitle there, it's a brief description of the origin and the very early history of the universe. Where do we start? Well, let's just think about what the universe looks like at the moment. That's a Hubble deep field. Perhaps we can actually use a three-dimensional representation rather than just a static two-dimensional picture to give us a better idea of what the universe looks like at the moment. This might look like a simulation of whole loads of galaxies and clusters of galaxies, but this is not so much a simulation, this is more a 3D atlas. The positions of galaxies have been noted in the sky and their distance measured through the redshift, the movement of the lines in a spectrum that gives us an idea of how fast they're receding and hence their distance according to the Hubble law. So all of that information has been put together into this model. So this is a 3D atlas of our local universe. Quite a few million galaxies have been plotted, and then we're sort of drifting through in a random path. So we can see there's lots of galaxies out there, and we see the galaxies aren't necessarily uniformly distributed. There are little knots and clusters in different places, and every once in a while we see what looks like a filament, a line of galaxies and clusters of galaxies. And every once in a while we see a region that seems to have rather fewer galaxies than anywhere else. So if we want to understand how the universe came to be, we have to have some understanding of how it came to look like it does here. So yes, a two-dimensional picture tells us something about the structure of the universe, and here, for instance, we can still, if we wish, measure the distances, but this is just a snapshot of a very small part of the sky containing a few thousand, perhaps up to 10,000 galaxies in the Hubble deep field. So what am I talking about? I'm talking about the creation of the universe. When did it happen? It happened 13.8 billion years ago. How long did it take to make a universe? Well, roughly speaking, it took about 3 minutes, and we'll see why that number crops up a little later. Where did the universe start? Some people say, can you point to where the Big Bang started? No, the Big Bang was the start of the universe, and therefore, by definition, it happened everywhere. Why did it evolve the way it did? Well, because of the laws of physics. As we understand them, if we start from a particular set of conditions, we should be able to apply the laws of physics and then work out why the universe looks the way it does now. How do we know all of this? Again, because of the laws of physics. If the laws of physics are wrong, then trash everything I'm going to say in the next hour or so. But if we believe the laws of physics, then we should be able to trace the evolution of the universe from the Big Bang to something close to the present day. So let me say a few words of introduction. Nature is not repetitive. If nature is repetitive, it would be very boring. If the same thing happened day after day, yes, with lockdown it sometimes seems that way, but if absolutely everything just repeated, then of course things would be very boring. And if nature was totally unpredictable, then it would be impossible to make any sense of the world. The reasons we can make sense of the world is because we can see certain patterns, not necessarily things repeating, but we see patterns that allow us to put structure on the way the world works. So nature is not repetitive, it's not unpredictable, it's somewhere in the middle. It's interesting. So we can ask the question, how does nature work? How does the universe work? How does the world work in the largest sense of the word? And we can paraphrase that as, what are the rules of the game? The universe has been set up in a particular way and it has evolved over 13.8 billion years. But what determines the rules of the game that tell us that's how the universe evolves? If we were dealing with a different game, this one for instance, we might ask, well, given this picture, can you work out what the rules of the game are? If you didn't know what chess was, if you had no idea what was going on, from this picture, can you tell what the rules of chess are? You could look at that and say, well, it appears to be moving, it appears to be a whole load of pieces on a board with a certain number of squares, and there appear to be two types of colours, but lots of different shapes. It's very difficult to work out what the rules of the game are, given that snapshot. And arguably it's the same if you were given this snapshot. Here's a picture of a galaxy. What is this galaxy doing? What are the rules of the game that dictate why the galaxy looks like that? From a snapshot, you can't tell. We know that galaxies evolve and rotate and do all sorts of other things. Stars are born and die within a galaxy. But we know that, for instance, the rotation of a galaxy might take hundreds of millions of years. So even if we watched it for the lifetime of an astronomer, we still wouldn't be able to tell how that galaxy is changing over billions of years because our lifespan is simply too short. So how do we get around that problem? Just like the chess problem, if we can't video a chess game, that would be ideal to watch an entire game from start to finish. Then we can start to build up an idea of what are the rules of the game for chess. But because we can't watch the universe evolve over billions of years, then arguably we shouldn't be able to watch a video of the chess game being played. So what's the alternative? Instead of watching a video of two people playing chess, an alternative is to take a snapshot like this, but not just one, take a snapshot of 1 billion games of chess which are all being played by different players and are at different stages of the game. If you were to take a snapshot of 1 billion games of chess and look at them all, then by putting all of that information together, you might be able to figure out what the rules of the game are. So just like one galaxy is not enough, we have to think about, can we statistically look at what's happening at the moment for not necessarily billions, but maybe thousands or millions of galaxies, and can we get an idea of how they're changing by looking at some young galaxies and some old galaxies. We have this advantage that when we look at more distant galaxies, we're looking back in time because of the length of time light takes to reach us. And so, for instance, with the Hubble Deep Field, we might be looking at galaxies as they were many billions of years ago. And by looking at more local galaxies, we can get an idea of how they might have evolved. So we still only have snapshots, but we have snapshots as a function of time. Not quite the same as watching a video that lasts 1 billion years, but it does give us an idea of how to put the rules of the game together so that we understand the rules of the game for the universe. We look out within our galaxy and things look very complex. This is just a snapshot again of a particular part of our local part of the Milky Way galaxy. We see some stars of different colours and we see clouds of gas and dust. Again, apparently different colours. We have some pink over here and blue over there and some brown dust down here. And it looks exceptionally complex. So how can we possibly work out what the rules of the game are where even a tiny part of our local backyard looks to be extremely complex? Doesn't complexity rule out the possibility of a simple set of rules? Well, let's consider an alternative. Here we have a mathematical collection of points, pixels if you prefer, in this image. It's called the Mandelbrot set. Perhaps some of you have heard of it. If we just zoom in a little bit and say, what would we see in this collection of pixels if we zoomed in? At some point, presumably, the detail will run out. Well, actually not so. This particular mathematical set of, if you like, coloured dots, if you want to think of them that way, is infinitely complex in the sense that, as you can see in this little cropped video, if we zoom in to a particular part of this set and ask at what point do we run out of detail, the answer is never. We can zoom in as much as we like, and the amount of detail within this structure, within this mathematical set of points, that amount of detail is effectively infinite. You might see features which look like they're repeating, like these motifs we can see in the video there. But strictly speaking, they're only similar. They're not actually repeating. Just like one star might appear to be similar to another star, but is not an absolute copy of it. So even though the structures inside this mathematical set of points appears to be very complex, and appears to have certain repeating patterns, they never actually repeat. And we can zoom in essentially as far as we like, and we will see more and more and more and more detail. So we can ask ourselves, okay, this is a mathematical or mathematically generated set of coloured pixels. and we've zoomed in by, or eventually we will have zoomed in by, a factor of probably more than 1 billion to get from where we started to where we are now. So how complex must the rule be in order to generate the entirety of these pixels? Not just the few million pixels that we've seen in the last few seconds, but how complex must the rule be to generate effectively an infinite set of coloured dots like this? Well, the point I'm making is, even though the collection, the structure, what we're looking at is infinitely complex, the underlying rule is actually amazingly simple. The maths required is that. That formula, if applied over and over again, will generate every pixel in the entire Mandelbrot set. Not just the ones we're looking at the moment, but the entire set. So if something as simple as a formula there which can be written down in a handful of symbols, if that can generate the Mandelbrot set, then we have to remember that complexity is not the same as incomprehensibility. We can comprehend how to generate something that is infinitely complex. And this is a point that Einstein made some time ago. One of the most incomprehensible things about the world is that it is comprehensible. Just because it's very complex doesn't mean we can't understand how it's put together. It doesn't mean that we can't figure out what the rules of the game are and hence understand why the universe is the way it is. So let's just have a little think about the flow of thought that gets us into thinking about the universe. We can make an observation, something like 100 years ago, galaxies appear to be moving away from each other. And from that we conclude that the universe is expanding. We can make other observations in the laboratory, as well as looking at what's going out there in the universe. We can do experiments in the laboratory. For instance, we can do particle physics experiments in an accelerator, such as the Large Hadron Collider at CERN, and that gives us an understanding of the building blocks of the universe, what particles are put together in order to make atoms, in order to make us, in order to make the Earth, in order to make the rest of the universe. We do, however, have to make some assumptions. It's not all just about observing the universe and doing experiments in the lab. We have to make some assumptions. And two of the assumptions are written down here. And one is that the laws of physics here are the same as the laws of physics there. In other words, the laws of physics don't differ at different places. It would be very difficult trying to figure out how the universe works if the laws of physics in England were different from the laws of physics in Australia, or the laws of physics on the moon, or the laws of physics in the next galaxy. And another fundamental assumption is the laws of physics now are the same as the laws of physics then. Again, if we said that it's okay for the laws of physics to change, so we do an experiment today and we work out that gravity pulls an apple towards the centre of the Earth, but then we find tomorrow the apple goes sideways rather than falls towards the centre of the Earth. If the laws of physics change as a function of time, then we have no hope of actually understanding what the rules of the game are, if the rules keep changing. If somebody keeps moving the goalposts, we can't understand what's going on. So there's the assumption that the laws of physics are immutable. They haven't changed, they're not going to change, and they're the same everywhere. If that turns out not to be the case, then we'll have to revise our understanding of how the universe works. So, based on the observations and the assumptions laid out there, then we conclude that the universe was created in a very hot, dense state 13.8 billion years ago, and ever since then it's been expanding and cooling. So the big question is, we look out there and we see a huge amount of stuff. In the observable universe, many billions of light years in diameter, we see a huge amount of stuff. Galaxies which appear to be full of stars and gas and dust and other things. Where did all of this matter come from? And we can ask the question, well, how far back in time can we go to the point of t = 0, if you like? We know that the universe is 13.8 billion years old. How far back can we go before we can say, well, I'm not altogether convinced that the laws of physics still apply as we understand them at the moment? So Are we okay for the first billion years of the 13.8 billion year history of the universe? Yep, no problem at all. What about the first million years? Yep, fine. First 1,000 years? Yep. What about the first year of those 13.8 billion years? Yep, we are quite happy that during that first year we know pretty much what was going on. What about the first day? What about the first hour? What about the first minute? What about the first second after the Big Bang? Do we think that the laws of physics we understand today were in force at that point? Yes, we do. What about the first millisecond? No problem. What about the first microsecond? What about the millionth of a second? No problem. What about the first nanosecond? Now we're talking a billionth of a second after the Big Bang. Yes, still fine. What about the first picosecond, the first trillionth of a second after the Big Bang? Maybe. That is the point at which our conviction that we know what's going on, that's the point that we are not quite sure that we can go back any further. In other words, before the first picosecond, we're on slightly shaky ground. From a picosecond onwards, we think, we being generic, not necessarily me, but scientists in general, believe that we've got a reasonably good understanding of how the universe evolved from 1 picosecond up to the present day, 13.8 billion years later. One of the reasons, which I'll come back to from time to time, is that we can do experiments that tell us we're on the right track, but we can't do any experiments that tell us what happened in the first picosecond of existence. But from there onwards, we're okay. So that was a very long and rambling introduction to give you an idea of where I'm coming from when trying to present this particular talk. I'm now going to cover a few basic ideas that we're going to build on to talk about what happened in the first fraction of a second, what happened in the first few seconds, what happened in the first few minutes after the Big Bang. Then we're going to make a jump, and we're going to jump 377,000 years. That might sound a rather arbitrary value, but there's a good reason for choosing that number. And then, of course, due to the time constraints, we're going to cover the next 13.8 billion years rather briefly compared to what we've been doing for the first fraction of a second, for the first few minutes. Okay, let's make sure we've got a few basic ideas that will be what we need to understand what's coming in the few seconds or the few minutes after the Big Bang. So firstly, we are made of atoms. I hope that doesn't come as a shock to any of you in the audience. We're made of atoms, and atoms are essentially little balls with a nucleus in the centre and a buzzing hive of electrons, if you like, orbiting. We don't have to worry too much about what quantum mechanics tells us about exactly how atoms are put together. Here we're more concerned with simply what the constituents are, the fact that we have a positively charged nucleus and negatively charged electrons buzzing around that nucleus. So an atom is made up of a nucleus and electrons. Electrons, as far as we know, are not made of anything. They are fundamental particles. You can't take an electron, cut it in half and have two bits of something else. As far as we know, an electron just is. But a nucleus is a compound particle. It's made up of other things. We could take a nucleus and, if we wished, we could break it down into its component parts, which are protons and neutrons. Similarly, protons and neutrons are not fundamental particles. They're made of something else. And for an example, I'm just going to take the proton. The proton, we believe, is made of three fundamental particles called quarks. And again, fundamental means you can't take a quark and cut it in half and then reveal whatever is inside a quark, as far as we understand it. In other words, our understanding of this particular Russian doll, if you like, goes as far as quarks and then stops. So by Russian doll, I'm talking about we're made of molecules, molecules are made of atoms, atoms are made of nuclei, and nuclei are made of protons. Nuclei are made of protons and neutrons, and for instance a proton or a neutron is made up of quarks. So we have this idea of a Russian doll. We can break it apart, look inside, break the components apart, look inside, etc. How much energy it takes, how much effort it takes to separate a whole load of atoms in a molecule, there's a certain amount of energy required to do that. but it takes more energy to take an atom and split it into its component parts. And it takes even more energy to take a nucleus and separate it into protons and neutrons. And it takes even more energy to take a proton and separate it out into quarks. In other words, there's an implicit energy scale here when we think about this Russian doll of looking inside, looking inside, looking inside. If we want to keep looking inside, it takes more and more and more energy for us to start with a complex system like a person or a molecule and to start tearing it to pieces. When a physicist talks about energy, as far as this talk is concerned, we can consider energy to be sort of the same as temperature. In other words, low energy and high energy correspond to low temperature and high temperature, or cold and hot. And remember, because we think the universe started as a hot, dense state and then expanded and cooled, that means time actually runs upwards in this particular diagram from hot to cold, from high energy to low energy. So what that means is, although we thought of it in terms of a Russian doll and looking inside, then as far as the universe is concerned, the universe was built from the bottom up, not from the top down. So in other words, if you start with fundamental particles, if you started from things that don't have any components, like electrons and quarks, then if the universe is too hot, you can't put quarks together to make a proton. If it's too hot, that proton will just shake itself apart and end up back in its constituent quarks again. You have to wait until the universe has cooled down a little bit before quarks can make a proton. And similarly, you have to wait until it's cooled even further before protons and neutrons can make a nucleus. Because if you don't wait until the universe has cooled down, the universe is too hot and the nucleus will shake itself apart and it will separate into its protons and neutrons. And similarly, you have to wait even longer before the universe is yet colder still until you can make atoms and then make molecules and then make people. So that's why this is labelled a few basic ideas, because we have this basic idea that if you start with a few particles, eventually those particles can, if you like, club together to make more complex systems, but it takes time because the universe has to cool, and the rate at which the universe cools dictates how these various structures are made. Protons, and then nuclei, and then atoms, and then molecules, and then us. Okay. So we can ask the question, what happened at the instant of t equals 0? Remember, we're on reasonably good ground from a picosecond onwards, but at t equals 0, we cannot provide a definitive answer. There is no known science that tells us what happened at the instant of the Big Bang. There's a number of theories out there, and one of the most popular is the fact that it was a quantum fluctuation. What is a quantum fluctuation? Well, quantum mechanics, which is the mechanics of telling us what happens on a small scale, typically a scale of sized atoms or smaller, it is possible to borrow something from nothing. That sounds like it goes against the rules of physics, but actually it doesn't. So it is possible to borrow energy, and if you borrow energy, that's just like borrowing matter, because energy and matter can be, if you like, swapped backwards and forwards according to E equals mc squared. So if you're allowed to borrow energy, you can make matter. Where do you borrow this energy from? Well, sort of nowhere. It's like having an ethereal bank from which you can borrow money. It sounds really weird, but then quantum mechanics is weird, and that's the topic of an entirely different talk. So we're just going to accept that quantum fluctuations do occur. We can actually effectively measure, or our understanding of quantum mechanics, our understanding of atoms and subatomic physics, is based on the idea that things can fluctuate and you can borrow from nothing, as long as you pay it back. How big can the fluctuation be? Well, you can borrow, in a sense, as much energy as you like from the bank of nothing, as long as you pay it back in a certain time. And there's a fundamental rule that says energy times time has got an upper limit. In other words, you can borrow a small amount for a long time, or if you borrow a very large amount of energy, you've got to pay it back very quickly. It's like a loan. If you don't want to generate interest, if you borrow a very small amount of money, you're not too fussed about paying it back because the interest will be negligible. But if you borrow £1,000,000 and you know what the interest rate is, it's obviously in your best interest to make sure you pay it back very quickly. It's as if you're borrowing from nothing, and that's okay as long as you pay it back before the universe has time to notice. That's one way of thinking of it. That's paraphrasing it somewhat, but that's one way of thinking of it. If you pay it back quickly enough, the universe doesn't notice that you borrowed it in the first place. So the key thing is, well, how much energy do we need to borrow to make a universe? If you add up how much energy there appears to be in the universe, try and work out how much mass is out there, and we know the energy equivalent of that, E equals mc squared, and we can work out how much energy there is based on gravitational energy. All of the mass energy is positive and all the gravitational energy is negative, and it might well be that the total is 0, or at least very small. If the total energy of the universe is 0, and we have energy times time has an upper limit, it might be that we have plenty of time. Maybe we have an infinite amount of time in which we have to pay it back. That's one way of thinking about the Big Bang. That's not necessarily right. That is a way that a number of individuals think, but it's at the moment impossible to prove that that is the way the universe began. Let's move on, and we're now going to move on to a time period with that many zeros in it. So that is 10 to the minus 35 seconds, an unimaginably early point of the universe. At this point, the universe has now expanded until it's about the size of a golf ball. Golf ball is a nice little analogy because it gives us an idea of the size, and by size I mean imagine that everything that we can currently see in the observable universe, so everything that's within tens of billions of light years of us at the moment, everything in the observable universe, how close were those at this particular point in time? All of those objects would have been inside a sphere the size of a golf ball. So we don't know if the universe was any bigger than that, so we're just at the moment talking about how close were all of the bits of the universe that are currently inside the observable universe. So the universe expanded from apparently nothing to the size of a golf ball in that particular time. And just like a golf ball, the universe at that point was not perfectly smooth. It had little dimples in it. And again, take these dimples with a pinch of salt. What we mean is the density of the universe was not perfectly smooth. There were tiny variations where a point over here was just a little bit more dense than a point over here. And there were variations in density throughout the golf ball itself. Eventually, when the universe is much, much, much bigger than a golf ball, those dimples are what effectively gives rise to the variations in density that will produce the large-scale structures, i.e. the superclusters and the clusters and individual galaxies. So without those dimples, we can't expect the universe to clump into the matter that we see when we look at the universe now. And now we arrive at the point of 1 picosecond, 10 to the minus 12 seconds. 1 picosecond after the creation of the universe has expanded to something of order the size of what we would now call the solar system. Of course, the solar system doesn't exist yet, just to give you an idea of scale. The temperature has been dropping all this time, and the temperature has now fallen to a rather balmy 10 to the power 15 Kelvin. And the energy of each of the constituents of whatever this stuff is made of, let's imagine this energy has made lots of quarks and electrons. These are fundamental particles. There are probably lots of other particles in this soup that's being made by this energy that we borrowed from nothing. But we call it a quark soup, even though it's made of quarks and electrons and probably other stuff as well. It's just a convenient name to remind us about this primordial soup that we're talking about. The energy of each of the particles in this soup is roughly the same as the energy that can be generated in the Large Hadron Collider. In other words, we can recreate the conditions using particles in a particle accelerator. That is why we believe that we can test our ideas from this point onwards. Now the energy is low enough that we can access this energy using laboratory equipment, using laboratory accelerators. Prior to this, the energies were so high we couldn't reproduce them in the laboratory. But from this point onwards, we can reproduce these energies, and hence if we have a particular idea of what's going on, we can test that in the laboratory. Matter and energy are continuously exchanging backwards and forwards. In a sense, you can think that we borrowed energy, but as soon as we borrow energy, we can make matter and antimatter. Antimatter is the opposite of matter. If matter, for instance, an electron, has a particular charge, its antimatter equivalent is an anti-electron which has the opposite charge. It looks very similar, it has the same mass, but it has opposite electrical charge. So matter and antimatter are generated by energy, and matter and antimatter make energy, and energy can make matter and antimatter. They exchange backwards and forwards, backwards and forwards. Any particular unit of energy can generate a certain amount of matter and the same amount of antimatter. And that matter and antimatter can annihilate and generate energy again. So if I use a big capital E as being a symbol that relates to energy, because I don't know what other symbol to use, then we know a certain amount of energy can generate matter and antimatter. Probably not oranges and anti-oranges, but the point is it doesn't matter what the matter is, if you'll excuse the pun. It doesn't matter whether we're talking about electrons and anti-electrons, or a quark and an anti-quark, or this particle and the anti-version of that particle. It's irrelevant at this stage what we're talking about. What matters is we borrowed energy, and from that we can make matter and antimatter. And almost immediately that those are made, they annihilate with each other and generate that same amount of energy again, which can then go on and make a different version of matter and antimatter. Again, probably not hot dogs, but it doesn't matter what the matter is. It generates some particle and its antiparticle. That's all that we need care about. But one of the key observations is that somehow something must have happened back in this very early stage of the universe, because for reasons we don't quite understand at the moment, although matter and antimatter you might expect to be made in the same quantity, somehow matter gained an excess over antimatter. So what that meant was a whole load of matter was produced, and not quite the same amount of antimatter was produced. Here I've shown it as 10 lots of one and 9 lots of another. In fact, it was more like 1,000,000,001 lots of matter compared to 1,000,000,000 lots of antimatter. The discrepancy was tiny, only about 1 part in 1,000,000,000. But if that's the situation you have, then matter and antimatter can annihilate to give you energy for all of these, but not the final particle at the end there. This 1 part in 1,000,000,000 hasn't got any antimatter to annihilate with. So what that means is you're left with a universe full of energy because of the matter annihilating to give you energy, but you're left with a little bit of matter left over. All of this energy ultimately ends up as radiation, as light, electromagnetic radiation of light of lots of different wavelengths, but we're left at the end of the day with some matter which has got no antimatter to annihilate with. And that is what's left over that makes up you and me and the Earth and the Sun and the solar system and the Milky Way galaxy, and as far as we can tell, every other galaxy in the observable universe is made of that leftover matter because matter and antimatter became out of balance. So be grateful for that 1 part in 1,000,000,000 that didn't quite have a partner to match up to. We're now racing ahead in time to about a millisecond, 1/1000th of a second after the Big Bang. Matter and antimatter are continuing, popping into and out of existence. Matter and antimatter to energy, energy into matter and antimatter. Protons and neutrons are made from constituent quarks, and they are transforming into each other in the sense that if we take 3 quarks that make up a proton, they can end up changing into a neutron. Because different quarks, it doesn't matter about the details of what these quarks are, a particular combination of certain quarks make up a bag that we call a proton, and a different arrangement of quarks is a bag that we call a neutron. Remember, proton and neutron are not fundamental particles, they are mixtures of other particles. So without worrying about why it is that they do that, we can say that a particular combination of quarks makes a proton and a different combination of quarks makes a neutron, and they are very similar energies, so protons can change into neutrons and neutrons can change into protons simply by rearranging the mix of quarks that are in this bag of three particles. And this continues on until we get to the point of about 1 second after the Big Bang. Now the universe has cooled, and we are getting nice and cool now, 1 billion Kelvin. That might sound ridiculously hot, but bear in mind that's not so far away from the temperature inside the core of some very hot stars. Now that it's cooled to only 1 billion Kelvin, remember our Russian doll idea and the idea of the universe cooling down, it's now too cold for protons and neutrons to readily swap back and forth. They can do that as long as there's enough energy for them to do that. But now the universe is cooling down, there's not enough energy for a proton to keep changing into a neutron and a neutron into a proton back and forth, back and forth. It just so happens that protons are a little bit lighter than neutrons. How do we know that? Because we can measure them in the laboratory. And there's no reason to believe that the protons that existed billions of years ago are fundamentally any different from the protons that we can measure in the laboratory. In a sense, that's one of the assumptions we're making. So protons are a little lighter than neutrons, only by about 0.1%, but because of that difference in mass, the protons end up outnumbering the neutrons. The universe can make lots of protons and lots of neutrons, but it ends up with a preference for the protons. In other words, nature always favours the lower energy, or in this particular case, the lower mass, which is effectively the same thing because of E equals mc squared. This is again a fairly fundamental property of physics. Given a choice, if you can make lots of things, you will generally speaking favour the lower energy or the lower mass. And because protons are a little bit lighter than neutrons, you end up with more protons than neutrons. It just so happens when you do the calculations, when you run the numbers, it turns out that if you start with a temperature of about 1 billion Kelvin, and if you have protons that are 1 part in 1,000 lighter than neutrons, you work the numbers out, a bit tricky, but you can work the numbers out. It turns out that you should end up with 3/4 protons, which are in red here in this diagram, and 1/4 of them will be neutrons because they're a little bit heavier. So there's a prediction there, if you like, based on if we understand physics, that's what we would expect to happen. After 1 second, we would expect 3/4 red and 1/4 blue when looking at the mix of protons and neutrons. If we move forward to something of order a couple of minutes or so, we know that neutrons are unstable. We know that neutrons can decay into protons. We see that again in the laboratory. We know it happens. There's no reason to assume it doesn't happen in the early universe. So the ratio of the protons to neutrons now changes slightly. Instead of what we had before, when 3/4 were red and 1/4 were blue, now we have the ratio of 14 to 2. 14 protons for every 2 neutrons, simply because some of them have changed. The universe, after 100 seconds or so, has now cooled, and the universe is now 100 million Kelvin. It is now cool enough that protons and neutrons can start getting it together. Remember, before this point, the universe was too hot, and any attempt for protons and neutrons to make a nucleus, it was simply too hot and the nucleus would immediately fall apart. But now the universe has cooled to only 100 million Kelvin, it is now possible for nuclei to form. And what happens is that the 2 neutrons hook up with 2 protons to make, on the right hand side there, a nucleus of helium, 2 blue and 2 red. And that leaves a whole load of bachelors. These 12 nuclei on the left-hand side haven't got any neutrons to pair up with. Protons would really like to get together with neutrons. The structure that is 2 protons and 2 neutrons is a very stable structure, and they would love to get together like that. But once those 2 neutrons have paired up with 2 protons, there's no more neutrons left for those 12 bachelors. And therefore we end up with a universe which is full of that much helium and that much hydrogen. In other words, again, we can basically make a prediction that that's what we would expect the universe to make up. Because after approximately 3 minutes, we can't expect that to change. The universe is not hot enough to start mixing things around. After 3 minutes, the universe is so cold, then the amount of hydrogen and the amount of helium is effectively now fixed. And so we can make a prediction. If our understanding of the universe is correct, then what we would expect is, if you look at the mass there, we would expect the number of nuclei, well, perhaps the number of nuclei is not so much important as the mass. If you look at the total number of circles on the left that make up hydrogen, that's 2, 4, 6, 8, 10, 12, so there's 12 units of mass there. And on the right we have the helium nucleus, which is made up of 4 of those circles. So we have 3/4 hydrogen, 1/4 helium. That's what we would expect the universe to be made of if we've understood the physics correctly. What do we find if we go and observe the universe and see, of all the gas that's out there, how much is hydrogen and how much is helium? We find that ratio. And that, fundamentally, is why we believe we've got the physics right. The physics makes a prediction about the hydrogen and helium, and that is what we observe. So we believe we've got the fundamental physics correct. 3 minutes makes a universe, and you could argue nothing interesting happens for the next 377,000 years. Why that particular number? Well, all through this 1/3 of a million years or so, the universe is continuing to expand and continuing to cool down, so the temperature is dropping. Eventually there comes a point where the universe cools to about 3000 Kelvin. That point is 377,000 years after the Big Bang. What is so magic about the temperature 3000 Kelvin? Well, it's important because at this temperature a nucleus can hang on to the electrons, a positively charged nucleus can hang on to negatively charged electrons, and so this is the first point that atoms can exist. Up to this point, 377,000 years after the Big Bang, no atoms existed. There were just various particles floating around. But from 377,000 years onwards, we have atoms. We have atoms of hydrogen and atoms of helium. That means that the universe changes from an ionized plasma. In other words, ionized means the positive nucleus and the negative electrons are separated, but now they've come together to make neutrally charged, uncharged atoms. For the first time in the history of the universe becomes transparent. Up to this point, the plasma has meant that photons of light have been essentially unable to move freely about the universe because they keep bouncing into positive charges here and negative charges there. But now we have atoms that have no net charge. Now photons can fly through the universe because the universe has become transparent. The light is released at this point. So light that was until this point trapped inside the plasma is now free to fly across the universe. And we see that light today, but much stretched out because the universe has expanded quite a lot since the point of 377,000 years. The universe is now some 1,000 times bigger than it was at this particular point at 377,000 years. The wavelength of the light is 1,000 times longer because the universe has expanded by 1,000-fold. At the time, 3000 Kelvin meant that the atoms were effectively white hot. If you take an object, it doesn't really matter what the object is, take the object, heat it up a few hundred degrees, it starts to perhaps glow red hot. Take it up to 3000 degrees, it will glow white hot. So the universe was white hot at 377,000 years. But now it's expanded by 1,000-fold, and that light, its wavelength, has been stretched 1,000-fold. What you get if you take light, which has a wavelength of a fraction of a micron, what happens if you stretch it 1,000-fold? you end up with light with a wavelength of centimeters or so, and you end up with microwaves. So the cosmic microwave background is the white hot glow of the universe back at 377,000 years, and that white hot light has been stretched into microwaves. So that, if you like, is a picture. It's an all-sky picture. You just map the entire sky and then unwrap it, just like you would with a map of the world. And then onto that you can say, well, it's essentially the same temperature everywhere, except there are fluctuations. And here we've exaggerated the fluctuations. Red are the slightly brighter parts of the sky, and blue are the slightly colder parts of the sky. Why are the temperature variations there? Well, remember the cosmic golf ball. When the golf ball expanded, there were dimples in it. There were variations in density and variations in temperature. And that effectively is what we're mapping out. So the cosmic microwave background is, in a sense, a picture of the golf ball expanded up to fill the entire sky in microwaves rather than in light or in density fluctuations, which we couldn't possibly have seen when the universe was only the size of a golf ball. So it's roughly the same intensity in all directions, but it's not perfectly smooth, and as I've just said, those small variations are effectively allowing us to see the dimples in the cosmic golf ball. And that's one reason why people are spending a lot of time looking at the cosmic microwave background. It's not just an oddity, it's not just a, oh well, it's there. If you study the cosmic microwave background, you are in a sense studying the early universe, and that's why it's so important. If we look at our local area around the Milky Way galaxy, it doesn't seem to have any particular structure when we look at our locality. There's the Milky Way in the middle, and we've got the Andromeda galaxy there on the bottom right, and various other small satellite galaxies, the Triangulum galaxy near the bottom there. But if we go out a little bit more in distance, and now the local group is just centered there in the middle of the diagram, now we can start to see that where the galaxies are structured, we see that galaxies are not uniformly distributed over three-dimensional space. There are quite definitely clusters and superclusters, and you also notice there's a hint of a filament there because the clusters seem to be lining up on particular lines. And if we go to an even larger scale where we can't see individual galaxies, but we get the hint of where most of the galaxies are situated, we can see that the universe around us is is mottled by these clusters that we can see, superclusters dotted around the place. And also we notice, for instance, on the right-hand side, we notice an area that seems to be completely empty of clusters. Again, reminding you that what we're looking at is effectively an imprint of the various dimples that were in the original cosmic golf ball, and then that led to variations in the cosmic microwave background. That's why we end up with galaxies here but no galaxies there, and a supercluster here but a void over here. It's simply the pattern that was made by the dimples, the variations in density that originally occurred in the cosmic golf ball that eventually gets imprinted as to how the galaxies look in our neighbourhood. We can look at a simulation and ask, well, if we simply start with a box, this is just a small part of the universe, if we start with a box which is full of hydrogen, helium, and we simply allow gravity to do its stuff, what do we see if we run a simulation? Well, if we allow gravity to grab hold of all of this hydrogen and helium, what we find is, if we do the simulations with accurate physics, we end up with this sort of cosmic web, these filament structures and these bright knots where the filaments cross each other, which is where the galaxies are forming. If we look at the same thing but just rotate it to make it a little easier to see the 3D structure, as gravity takes hold and the relatively uniform arrangement of gases end up collapsing into these filamentary structures, we end up with a cosmic web which ultimately form the galaxies, the clusters of galaxies and the superclusters of galaxies. I'm not going to spend time on exactly how that process works because, again, that's the topic of a different talk, how we go from the hydrogen that we've talked about here in the beginning of everything to how do we end up with a spiral galaxy that looks like the Milky Way, for instance. But what we end up with is a view of the universe that looks a little bit like this. This is a large-scale simulation called the Millennium Simulation. If we look at this sort of cosmic foam, if you like, and blow it up stage by stage by stage at different length scales, we can start to see that the foam can resolve itself into filamentary structures and a few voids where you don't seem to get much at all. And where you look at where these filaments cross, you get these high densities, which is where galaxies and clusters of galaxies and superclusters will form. And we can see that if we use this little video on a large scale, billions of parsecs or billions of light years across, the universe looks very uniform and looks a little bit like a sort of foam structure. If we zoom in this particular simulation to smaller and smaller length scales, from billions of parsecs or billions of light years down to a few million parsecs or a few million light years, we see these various filaments, and where the filaments cross we get these little knots, and this is where the matter is inflowing down the filaments and starting to form the structures that we recognize as galaxies and clusters of galaxies. Even on this scale, we're not at the moment looking at individual galaxies, we're still looking at clusters of galaxies. We'd have to go right down to the megaparsec sort of range before we can start to resolve individual galaxies within these clusters. So again, I'm not going to talk about the details of the dynamics of how those galaxies are created, but ultimately, if we start with a universe full of hydrogen and helium, we can eventually produce the sort of structures that we recognize as the structures we see. Remember the first video I showed where we had a three-dimensional atlas and we look at where all the galaxies are, and we find the galaxies are not uniformly spread, they're clustered, and the clusters tend to form on filaments, and there are some regions which are voids in which the galaxy density seems to be very low. So very briefly, what about the next 13.8 billion years? Well, once we have hydrogen, then essentially if we have a universe full of hydrogen and a little bit of helium as well, then we can understand in principle where galaxies come from, where stars come from. We can then understand planets, and then we can understand trees and mountains and snowflakes and rainbows and cats and okay, maybe not cats, because I don't think anybody really understands cats. But if you start with enough hydrogen and allow gravity to do its stuff, then basically you can understand how the rest of the universe comes together. Yes, there are some details of cosmic evolution that are yet to be worked out. Some of the real nitty-gritty details of galaxy dynamics, how a collapsing cloud of hydrogen ends up with a galaxy that might be a spiral structure, or how do we understand the various elliptical galaxies that exist. We can start with hydrogen, and we know that we're on a fairly solid footing to understand then, using simulations and other physics, to see how we can understand the development of galaxies. If we remind ourselves on what the timeline is, this timeline is a little bit ridiculous because it's got giga-years on the right-hand side, and there's now at 13.8 giga-years, but on the left-hand side it starts at this ridiculous 10 to the minus 35 seconds. So we said the universe comes into being, and at 10 to the minus 35 seconds it's expanded until it's about the size of a golf ball, and the dimples in the golf ball will ultimately give rise to the structures in the universe. The energy that we've borrowed from nothing can be used to make matter, such as electrons or quarks or other particles, so we've described that perhaps just as a quark soup of particles, changing into each other all the time because energy and matter keep changing backwards and forwards. After a fraction of a second, some of those particles, some of those quarks, can make protons and neutrons, and after about 3 minutes those protons and neutrons have gathered together to make helium, where the protons and the neutrons combine, and any protons that are left over that can't find a neutron partner just end up as a single proton, which is the nucleus of a hydrogen atom. So after 3 minutes the universe has made all of the hydrogen and helium that it needs. Nothing much happens until a fraction of a million years later, at which point the nuclei grab hold of any electrons that are floating around, and the positively charged protons end up collecting negatively charged electrons to make uncharged atoms, at which point the universe becomes transparent and the light is released to give us the cosmic microwave background at rather less than 1 million years. Nothing much happens for a while because it takes time for the hydrogen to make stars. It takes time for gravity to do its work and to make these cosmic filaments in the cosmic web, and ultimately that matter drains down the filaments and makes galaxies and makes stars. But it takes millions of years to do that, so for a while no stars exist, and then at some point stars are born, and then the universe lights up again and ultimately produces the galaxies that we see, both close galaxies that tell us what's going on now, and the more distant galaxies that tell us what happened a few billion years ago. So yes, there are still some problems. The jigsaw is not as complete as I perhaps have made out. Yeah, we found the corners, we found the edges, we've got most of the landscape, but there are still some pieces of sky missing from our jigsaw. There are some fairly big questions that still remain. Why exactly did matter win over antimatter? If they were made in equal amounts and they stayed symmetric, then the universe would be full of light and there would be no matter because it would have annihilated with all of the antimatter. So we can be grateful that matter did win over antimatter, but we don't know why. We don't know fundamentally what caused the asymmetry that led us into a universe that has got a lot of light in it, but also a shed load of matter as well that's still floating around, and as far as we can tell, everything we see around us is made of matter rather than antimatter. And of course I've completely ignored the fact that there's a whole load of dark matter out there as well. I've talked about hydrogen and helium and how we've tested that we get the right amount of hydrogen and helium, but that's not all there is. Apparently there's a whole load of dark matter out there. How do we know it's there? Because galaxies, for instance, rotate at the wrong speeds, and clusters of galaxies hang together, whereas you'd expect them to have flown apart based on how much matter there is, how much gravity there appears to be inside a cluster. So there must be some additional matter that's holding clusters of galaxies together and holding the stars inside galaxies, but we don't know what that is. And even more enigmatic is dark energy, causing the universe to expand and accelerate. So we can understand that the universe was born in a big bang and has been expanding ever since, but you might have expected that because gravity is trying to pull everything together, surely the expansion should be slowing down as the universe expands. And it did for a while, but now it appears to be accelerating. Something is pushing things apart, and it's overpowering gravity, trying to hold things together. So what is the nature of dark energy that is doing that? We don't know. So I naively called this talk the beginning of everything. But whilst talking about everything, in the early part of this talk, I tried to make it clear that by everything we meant everything that we can see. Everything that we can see in the observable universe. We look out into a sphere tens of billions of light years across and we see galaxies and stars and dust and gas. That is what I was referring to when I was talking about the beginning of everything. But as I've just stated here, that is not everything, because the ordinary matter in the universe that's made up of atoms and things we recognise is perhaps only 4% of the total content of the universe. Only 4%. The other 96% is still a bit of a mystery. But, as they say, that's another story. Thank you all for listening.